So now we've seen that in solving a differential equation, we get, as I called it before, a family of solutions, either through an additive constant plus c when we're dealing with a differential equation where the derivative depends only on the independent variable, or in the case where we saw examples where it depended on the only on the dependent variable, we ended up with a multiplicative constant c. So that then tells us that we've seen differential equations can have an infinite number of solutions where we can choose that c value to be whatever we'd like. But if we're given extra information in the form of a point that the that the solution function must pass through, then that's enough for us to then narrow that family of functions down to a single function. So this idea of giving us this point that the function must satisfy is called an initial condition. So we're going to say here that a differential equation with an initial condition is called an initial value problem. We're often going to encounter problems where we do have that initial condition. So we're going to see a lot of initial value problems. And for shorthand, I'll point out that these are often referred to as IVPs. So it has a differential equation, but it gives you an extra piece of information about the solution. So to make this clear, we could see this with the following example. If we look at dy dx equals y, and suppose that I have the extra knowledge that y of 0 is 2. So this is what we mean by an initial condition. This is telling us not only does y satisfy the differential equation, but the solution we're looking for also passes through the point 0, 2. So the general solution to the differential equation, as we observed in the previous video, is the function y equals c e to the x. And if you think about that type of function, right, we can see that if I were to graph, say, just like 1 e to the x, we could have that. I could scale it with lots of different constants, and we could have things like that. If the c value were negative, it would look like this. And even if the c value were 0, we'd actually get the constant function y equals 0. But that's just dealing with this part. So that's why we get infinitely many possible solutions to that. So the way that we deal with initial value problems is typically we handle the solution first, and then I can go back and try to satisfy the initial condition. So now I have, this is the general solution. Knowing that y of 0 needs to be 2, well, let's plug x equals 0 into our boxed general equation. That tells us that c e to the 0 is equal to 2. Because e to the 0 is 1, that tells us c is equal to 2. So in this case where I have this initial value problem, my answer is just going to be one specific function. We said c would be 2. So we know that this is the solution to this initial value problem. So we kind of go through this in stages, first dealing with the general solution and then specifying any constants we've introduced. So another thing that I want to cover here, we've now seen in the scope of the idea of solutions, it's much easier to check that a function is a solution to a differential equation than to come up with a solution on our own. But I want to talk about different kinds of solutions. So among all types of solutions, we can say that constant solutions to a differential equation, we're going to see that these are much easier to find, and we call these solutions equilibrium solutions. Okay. So looking at just my graph above where I graphed several possible solutions in the last example, we see that there's a lot of similarities to the solutions, except when we had the solution y equals 0. That was very different than the other in this class of functions. That's an example of a constant solution, right? We get a horizontal line, we get the y value is constant. And so we do separate those, but also the way that we define these as constant solutions makes it much simpler to come up with these. So solving the differential equation in general is often difficult, but we should always be able to come up with equilibrium solutions. So I'm going to say find all equilibrium solutions, and we'll go through a few different differential equations. I'll also point out the equilibrium solutions. This is separate from initial value problems. We're not focusing on that here. So if the first one I have dy dx equals k times y, the second one dy dx equals y times 2 minus y times 1 plus y times x minus 3. And then we'll look at dy dx equals y squared plus 1. So before we answer these, I want to point out that constant solutions, that's what we're looking for. That means that we're looking for y equals c for some number, some constant. Well, then what you know has to be true is that dy dx is 0 because the derivative of a constant is 0. So when I'm trying to solve for constant solutions, I want to treat my dy dx as 0 and try to find any y values that would cause that to be true. So up here in this first one, if I set 0 equal to ky, I'll put the colon here, that would mean, because again, we're solving for y values, k is some constant. The only way that's going to happen is if y is 0. So we would have one equilibrium solution to this, and this is like a specific example above here where we saw that. For this one up here, again, my approach would be to set 0 equal to the right-hand side. And we're trying to solve for y values that force this to be true. And note here we get 3 equilibrium solutions. So sometimes you have multiple equilibrium solutions. The other thing I wanted to point out here, notice that I don't list x equals 3. Of course, x equals 3 does satisfy that this is equal to 0, but we're trying to solve for constant solutions to the differential equation. Solutions are functions y equals x, y equals f of x. So we're trying to look for where the y values are constant here. So you would ignore any roots where you're focusing on a constant value of x. And then finally, this last one, again, we would set 0 equal to y squared plus 1. And notice that in this instance, it's not possible for y squared plus 1 to equal 0. So what we're seeing here is that sometimes you'll have one where there are no equilibrium solutions. So you could have just one, you could have multiple, or you might have no equilibrium solutions at all. But the key thing is it should always be relatively simple to find any equilibrium solutions. Solving for the general solution to a differential equation can be quite complicated.